All right, so today we're going deep, deep into the world of Giorgio Parisi, a physicist who, well, he just isn't afraid to tackle the messy stuff. And if you're interested in behavioral physics, well, stick around, because Parisi's work might just hold some key insights.
You got that right. Palisi won the 2021 Nobel Prize in Physics, and he's famous for his work on things like spin glasses. But, his research goes way beyond that. I mean, we're talking neural networks, climate science, even, get this, the collective behavior of birds.
Okay, so I'm picturing, like, a guy with a chalkboard, right, covered in all these crazy equations, but also maybe a telescope pointed at a flock of starlings. It's a lot, honestly. I mean, where do we even begin with someone who seems to bridge so many different areas of science?
Well, one of the things that really makes Parisia so unique is his fascination with what we call disordered systems. So think of a magnet, but like all the little magnetic bits are jumbled up instead of being all neat and lined up. That's the kind of complexity that Parisi loves to dive into. He's trying to find the patterns hidden within the chaos.
Hmm. I think I'm starting to understand why his Roman students nicknamed some of his work spin glass theory and beyond. So tell me, what exactly is a spin glass? And why would anyone want to study something that sounds, well, kind of messy?
Okay, so imagine a crystal. It normally has this very, very orderly structure, but now let's sprinkle in some magnetic impurities, just randomly. Now those impurities are going to interact with each other in all these unpredictable ways and create a magnetic state that's, well, it's all over the place. That's a spin glass. And it's a classic example of a disordered system.
So not your typical bar magnet then. Sounds like a total nightmare to try and make sense of. How do you even start to study something that's inherently random like that?
Well, that's where Parisi's genius comes in. He developed this tool called the replica method, and it's basically a mathematical way to analyze these systems that seem so chaotic. So imagine making a bunch of copies, like replicas, of the same spin glass system. Each replica, it starts in a slightly different configuration, and by studying how those replicas evolve and comparing them to each other, well, we can start to learn some things about the overall behavior of the system.
Okay, so instead of just looking at one messy system, he's looking at a ton of slightly different messy systems and trying to see what they have in common. Clever. But did his theories actually hold up in the real world?
They did. One way to test these theories is through computer simulations, and we can do that using a simplified model of a spin glass called the Sherrington-Kirkpatrick model. So think of it like a virtual spin glass. What's amazing is that the simulations really did match Parisi's theoretical predictions.
Wow, so he was able to predict the behavior of these crazy complex systems just using math. Okay, I'm starting to see why he won a Nobel Prize.
Yeah.
But you mentioned that spin glass theory and beyond, right? What else has he tackled? How do you even go beyond something as complex as spin glasses?
Oh.
Okay, so we've definitely established that Parisi, he is a master of finding order in all that chaos.
Hmm.
But his work, it goes way beyond just spin glasses, right? And it feels like he's always jumping between completely different fields.
Yeah.
Did that somehow influence this unique approach he takes?
Absolutely. I mean, Parisi's career path, it's almost as fascinating as the research itself. He started in Rome, a city steeped in physics history. In fact, he even studied at the same university as Enrico Fermi and that famous group, I Ragazzi di Via
Wait,
Panisperna.
hold on. Those are the guys who basically, like, they kickstarted the whole nuclear age, right?
Sort of.
Talk about some big shoes to fill. So did he follow in their, like, exact footsteps?
Well, he definitely shared that same passion for physics, but even early on, Parisi's interests, well, they kind of extended beyond those traditional areas that were like really big in Rome at the time. I mean, he spent some time at a major physics lab in Italy, but his like thirst for knowledge, it quickly led him beyond Italy's borders.
Hmm. So where did this, like, scientific globetrotting take him? Was there some kind of, I don't know, a hub for disordered systems research?
Not exactly, no. His first stop was Columbia University in the US back in the 1970s, and that was a time of like huge excitement in particle physics, the study of, the universe's tiniest building blocks.
So he went from this messy world of spin glasses to the, like, super precise world of particle physics. It seems like a big shift. What was he working on there?
So he joined this theory group that was really focused on quantum field theory. It's basically a framework for understanding like the fundamental forces of nature. And you know what? He actually published some really important papers during that time, kind of laying the foundation for, his future work.
Well, that's impressive. He didn't just, like, dip his toe in. He really, made a splash.
Yeah.
But how did this detour into the world of quarks and leptons and all that, how did that influence his return to, those messy systems?
It's hard to say for sure, but it's clear that exposure to all those different ideas, different approaches, it definitely broadened his perspective. This was a time when quantum field theory was being applied to a wider range of problems, including, the study of matter itself, which, well, that's where those disordered systems come in.
Ah, I see, I see. So maybe those seeds for his, like, later breakthroughs, they were planted even when he was still super focused on particle physics. So what happened after Columbia? I don't know, did he just keep chasing those, like, fundamental particles?
He did, yeah, but in Europe this time. He spent some time at some prestigious institutes in France, places that were really known for, like, their focus on really fundamental research and that really collaborative atmosphere. I mean, it's almost certain that he encountered like tons of new ideas, new perspectives that ended up shaping his work on disordered systems.
So he was, like, on this grand tour of physics knowledge, just absorbing the best from each place he visited. Did he, I don't know, make any breakthroughs while he was in France?
Yes, actually. He made a pretty big contribution to particle physics. He developed this set of equations. They're known as the DGLP equations. And these equations, they describe how the distribution of particles within protons and neutrons, how that changes depending on the energy at which they're observed.
So even when he was, knee-deep in that world of particle collisions, he was still making, like, really important discoveries. But I thought we were talking about, like, his shift towards statistical mechanics. Was he somehow working on both particle physics and disordered systems at the same time?
He was, yeah. Parisi is well known for his ability to juggle all these different research interests at once. And remember, even within particle physics, he was already exploring ideas related to random matrices. And those, well, they have connections to those messy, disordered systems he's so fascinated by.
It's amazing, even when it seemed like he was taking this detour, he was still somehow, like, laying the groundwork for his later work. It really shows how interconnected all this scientific knowledge really is.
Absolutely. And it really speaks to Parisi's intellectual curiosity and his knack for spotting these connections that other people might just completely miss.
But eventually, he did shift, like, more decisively towards statistical mechanics, right? When did that happen?
It happened when he returned to Italy back in the early 1980s. He became a full professor at the University of Rome, Tor Vergata, and that's really when his focus turned to those disordered systems.
It seems like, coming back to his roots, it really marked a, turning point in his career. What was it about disordered systems that really, drew him in so strongly at that specific time?
Well, it's hard to say for sure, but it is worth noting that the study of disordered systems, well, it was gaining a lot of attention in the physics community right around then. There were a ton of unanswered questions and, a lot of exciting challenges to tackle.
So he was drawn to the frontier of a, rapidly developing field. That makes sense. He brought all those, tools and perspectives from his travels, and he applied them to this, really exciting new area of research.
Exactly. And remember the Sherrington-Kirkpatrick model we talked about earlier, that simplified model of a spin glass? Well, Parisi's work on that model, it led to a truly groundbreaking discovery.
Oh, yeah, the virtual spin glass, right. Remind me, what was it that he, discovered about that model?
He found that the low temperature state of the SK model, it's unbelievably complex. It doesn't just settle into a single predictable state like a normal magnet. Instead, it can exist in many possible states, each with its own unique properties.
Okay, so instead of just a simple organized magnet, we have this system that's just full of possibilities, like a landscape of all these different magnetic states. It's almost like a choose-your-own-adventure book, but for magnets.
That's a great way to put it. And Parisi actually developed this way to, understand and analyze this whole complex landscape. He called it replica symmetry breaking.
Replica symmetry breaking. So not only is he creating these replica systems, but they're, breaking symmetry rules. I'm confused.
Well, think of it like a landscape with tons and tons of valleys. So the spin glass system, it can get stuck in any one of those valleys, and they're all slightly different.
So the symmetry, it's broken because there's no one, correct valley for that system to settle in. It's there's no one answer, just a bunch of different possibilities.
Exactly. And Parisi's work, it provided a way to kind of make sense of this seemingly chaotic situation.
That's incredible. But was this all just theoretical? Did anyone actually, observe this replica symmetry breaking thing in a real physical system?
They did. And this is where it gets really exciting, honestly. Parisi's theoretical predictions, they were actually confirmed through those computer simulations we talked about.
So they basically built a virtual spin glass, right, inside a computer. and they saw this like crazy complex behavior play out. That's a powerful validation of his work.
It really is. It shows how theoretical physics can lead to, real world insights, even if those insights, well, they're happening in a virtual world.
Okay, so we've seen how Parisi's like journey took him from the precise world of particle physics to that messy world of disordered systems,
Hmm.
and how he made groundbreaking contributions to both. But I'm really curious to know more about the impact of this work beyond just the world of physics. Where does the beyond come in? Okay, so we've like really explored Parisi's journey, right?
Yeah.
And all that groundbreaking work on, those messy disordered systems. Now I got to know, how does this all connect to like the wider world? You mentioned neural networks, optimization problems, even like flocks of birds. I mean, how do those seemingly totally unrelated things tie back to, spin glasses?
Hmm. Well, let's start with those neural networks. They're basically mathematical models, right?
Yeah.
And they're inspired by how our brains work. And we use them for all kinds of things these days, like recognizing faces in photos to translating languages.
Right, right. Neural networks. They're a big, big deal in like artificial intelligence these days. But what do they have to do with, this whole chaotic world of disordered systems? It just seems like such a leap.
It might seem like a leap, yeah, but it's really not. Think about like how our brains are actually structured. We've got billions of these neurons, and they're all interconnected in this like incredibly complex web. And the strength of those connections, well, they can change over time, right? So it creates a kind of disorder within the network itself.
So you're saying our brains are actually like kind of like spin glasses,
Mhm.
full of all this like randomness and complexity.
In a way, yeah. I mean, yeah. And Parisi, he recognized that the tools he developed to study those spin glasses, they could also be applied to understanding these super complex neural networks.
That's pretty wild. So he used his knowledge of like messy magnets to help us like understand the human
Ah.
brain.
Hmm.
Did he like make any specific breakthroughs in that area?
He did, yeah. Parisi, he used that replica method, right, to analyze a type of neural network that we call the Hopfield model. And these models, well, they're used to study how our brains, how they store and retrieve memories.
So he was basically using like physics to unlock the secrets of memory. That's incredible.
Hmm.
What did he find out?
One of the key things his work helped to determine was like the storage capacity of these Hopfield networks. So essentially, how much information they can hold is kind of like figuring out the maximum memory capacity of a brain.
Wow, from spin glasses to the human brain. It's hard to keep up with all these connections. You also mentioned those optimization problems, right? How do those fit into this whole picture?
Well, optimization problems, I mean, they're everywhere in our lives. It's all about, finding the best solution out of like a ton of possibilities.
Okay, can you give me an example of something I can relate to?
Sure. So imagine you're like a delivery driver
Yeah.
and you got to drop off all these packages at a bunch of different places all over a city, right?
Yeah.
You want to find the shortest, most efficient route, right? That's an optimization problem.
Ah, okay, I get it. It's like trying to plan like the perfect road trip. But what do delivery routes have to do with, spin glasses?
Well, Parisi and his colleagues, they realized that the tools that they developed to study, like, the complex energy landscapes of those spin glasses, well, they could actually be applied to these kinds of optimization problems too.
So they use their knowledge of how those messy magnetic systems settle into different states to, like, optimize delivery routes. Wild.
Exactly. They came up with these new algorithms, inspired by their work on disordered systems. And those algorithms could solve these problems, like, way more efficiently.
I'm starting to see how this all, like, connects. It's like Parisi has this, I don't know, this toolbox full of all these mathematical techniques, and he's just not afraid to apply them to all sorts of, problems that seem totally unrelated.
Yeah, that's a great way to put it. And that actually brings us to, the birds. Remember those flocks of starlings? The ones that create those, like, mesmerizing, swirling patterns in the sky?
Oh yeah, those are so cool. It's like watching a living cloud. It looks totally chaotic, but somehow also like beautifully coordinated all at the same time. So what do flocks of birds have to do with spin glasses?
So Parisi and his team, they wanted to understand how these huge flocks, I mean, sometimes they have like thousands of birds in them, right? How did they manage to move together so seamlessly? It's a classic example of what we call, collective behavior.
Right, it's like they're all following some like invisible set of rules or something. But where does the disorder part come in?
The disorder is in like the individual movements of all the birds. Each bird, it's reacting to, its neighbors, making these tiny adjustments to its flight path. And there's no like single leader telling everyone what to do. It's just all these, these local interactions.
So it's kind of like a spin glass.
Yeah.
Where like each individual, magnetic spin is influencing its neighbors, and somehow all this like chaotic interaction leads to, an overall pattern.
You got it. And honestly, one of the most amazing things that Parisi's team discovered is that starlings, they interact based on something called topological distance rather than, just metric distance.
Okay, I'm gonna need you to break that down for me.
Yeah.
Topological distance.
Ah,
That sounds pretty complicated.
Okay, so it basically means that a starling, it pays more attention to its immediate neighbors, the birds that are right next to it, regardless of how far apart they are in terms of like actual, physical distance.
So it's like, I don't know, being on a crowded subway.
Yeah.
You're more aware of the people that are like packed in right next to you, even if someone standing, farther down the car might technically be closer.
Uh-huh. That's a perfect analogy.
Yeah.
And this helps to explain how these massive flocks, how they can maintain, cohesion and react so quickly to like changes in their environment, like, if a predator shows up.
That's incredible. So even the seemingly chaotic behavior of a flock of birds, it can be understood using these tools from physics, specifically the ones developed to study those disordered systems.
Exactly. It's another example of Parisi's ability to see these connections between things that seem, totally unrelated.
This whole deep dive has been, like, honestly mind-blowing. We've gone from this microscopic world of spin glasses to the macroscopic world of, bird flocks and everything in between. It really highlights how Parisi's work has, it's broken down all those traditional barriers between scientific disciplines.
It really is a testament to, the power of curiosity, creativity, and just like the willingness to really venture beyond, those traditional boundaries of those disciplines.
Parisi's story, it shows us that these seemingly totally different phenomena can share these underlying principles. And the tools that we develop for one area, well, they can unlock these like surprising insights in others.
It really makes you wonder what other like complex systems might benefit from, from Parisi's approach in the future. What new connections are out there, just waiting to be discovered?
That's a great question to think about. I have a feeling Giorgio Parisi's work is going to continue to inspire, generations of scientists to find those answers. Thanks for, taking us on this incredible journey. It's been a privilege to learn about the work of this remarkable physicist.
Oh, the pleasure was all mine. And to all our listeners out there, if you're feeling inspired, I really encourage you to explore some of Parisi's publications. You never know what fascinating connections you might uncover.
That's great advice.
Yeah.
Thanks for joining us on the deep dive.
Yeah.
And until next time, keep exploring.